Here we go, here we go. Not this time, but I do like for heat. I watched it for season 2.
Every time?
Only when I need it. But when I needed it, it helped. It saved me there.
Just in case.
You know, the few times that you need it is when you save it.
Can you write a little bigger?
Yeah, actually, that's one thing I really can do. But
Just
what
read.
I got there doesn't really matter. What we're doing is we're imagining we have a benzene toluene stream here, and we're trying to separate it, and benzene's more volatile, toluene's less volatile. So I put it in here to a stage, and I boil off half. So if this is 1 unit coming in, that's a half a unit going up, and that's a half a unit going down. I get up here, I condense half. So I get a quarter coming up here, and I get a quarter coming down here. And so I continue this. And here's what you're supposed to observe.
Wait, can you restart? I didn't follow anything you said.
That's okay. You'll pick up on it. You're a bright kid. It'll come to you like that. I notice I have 50, 50, 58, 42, 68, 32, and so on and so forth. I'm clearly increasing the benzene composition as I go. I have 50, 50. I got 42, 50. I got 32, 68. I'm clearly decreasing the benzene composition as I go down. I'm clearly on my way to making 100 benzene, 0 toluene. I'm clearly on my way to making 0 benzene, 100% toluene. However, there's a flaw. The flaw is that I've got all these streams here I haven't decided what to do with. And this is going 1, a half, a quarter, an eighth, a 16th. So in the end, I'm not making any. So we haven't really got a distillation column going yet until we decide a few more things. So our aim here is to convince ourselves that we know why distillation columns look the way they do. Why do distillation columns look the way they do? Now, if you want to see one, you can go over in the lab almost any day of the week.
No, they don't.
And there are people running distillation columns.
Do they?
Walk up to them, ask them any questions you want. See if they can deal with your questions. But whatever else you do, look over the operation, and you will see that it's going to look about the way we're going to decide it ought to look. And I think you ought to try and embarrass them if you can. Why not? Okay, so here's our problem. Schematically, without numbers, here's what's happening.
What the hell is this?
I have this stage right here. I take this stream off. This has been enriched 1 time in benzene. This has been depleted 1 time in benzene. Here's the feed. I feed this in here. This stream has been enriched twice in benzene. This stream has been enriched once, depleted once. This stream here goes here. This stream has been enriched twice, depleted once. This stream's been enriched 3 times. It's a schematic of what's going on. Now we stop and we look at this. And we say to ourselves, look at this guy here. He's been enriched twice, depleted once. He's got to be richer than this stream here, who's been enriched once, depleted once, and yet this guy is in equilibrium with this guy.
Is that mine?
So Yeah.
Is that a minus? Are you subtracting them, or do you just
Nah, it's just a dash.
Okay, all right.
So clearly, this guy, if he were in contact with this guy would be enriched even further. So it looks like what I ought to do is I ought to stick that string back in here. If I do that, the following good things happen. First, this stream becomes richer, and so this stream becomes richer because of equilibrium with that guy. That's one thing. Second thing that happens is that I no longer need to remove heat from that guy in order to get this guy. Putting this guy in will supply that guy. So I'm saving myself a heat exchanger there. And lastly, if this guy is about equal to this guy, this flow is about equal to that flow, and this is no longer 1/2, 1/4, it's more or less 1/2, 1/2. So I get three good things happening to me by just doing that one move. And further, I'm not throwing anything away. So let's sketch what we think a distillation column looks like, and let's see if we can attach meaning to the various strings. Here's the way it looks. I've got a column here with a bunch of stages in it. And I'll just indicate them schematically like so.
This is yours?
I'm going to put the feed in somewhere. So here goes the feed. I'm going to have a vapor rising through the column coming out here, and I'm not going to add or remove any heat inside this column. But when I get up here, I'm going to have to do something, so I remove some heat here, QD less than 0, and condense some of this. Take the rest as product. This I put back in, and the liquid flows through my column, keeps flowing through my column, keeps flowing through my column, keeps flowing through my, keeps flowing through my column, comes out the bottom, and there I put heat in, QB. Heat this, heat QB, vaporizes some of this, sends the vapor up the column like so. This stream coming back, some of it's vaporized going up, the rest comes out as product. So I got a product stream flowing here at a flow rate D and a composition, say YD. I call it YD because that's, I probably have to put an arrow over it. That right there is what is called a partial condenser. You go out and look in the lab, they don't have any partial condensers. We'll fix that up in a minute. This down here is a reboiler. It's called a reboiler. It's taking this liquid that's already been boiled once and sending it back up the column where it's condensed, sent back down, it's boiled, sent back up the column. This is a flow rate B and a bottoms product XB. I probably have to stick an arrow over it. This is a feed rate F, a feed composition Z, and this is what my column looks like. Now, here's what's happening. In this section right here, above the feed, this vapor going up is stripping the volatile out of this liquid coming back. So this vapor going up is picking up volatile from this liquid going down and carrying it up the column. In this section of the column right here, what's happening is that this liquid going down is absorbing the less volatile from this vapor going up, moving the less volatile downward. So I got two sections of this column. This one trying to move the vapor, try to move the volatile upward. Here we're trying to move the volatile like that. And here we're trying to move the non-volatile like that. And that is called a distillation column. Yeah, what's the question?
So how does the schematic actually look?
Just like that.
But you have one stream intersecting with the other stream in your schematic.
I'm not quite sure what the,
how does
a
it
better
look inside?
picture of a stage is something like this. better picture of a stage, there are all kinds of ways people do this. Out in the lab, what they've got is, okay, so here is what is called a downcomer from the stage above. Liquid's flowing down here. And then you put a weir here, and the liquid flows across like this, and then it goes down the downcomer. Now, what's happening to the vapor is that the vapor is coming up through here, and what they put on these plates, well, over in the lab anywhere, is they put bubble caps on. It looks something like this. Okay? These bubble caps are spring-loaded things, so that when the vapor builds up enough pressure, the spring, the cap is pushed up, the vapor comes out around, bubbles through this liquid, and proceeds on up the column. That is represented by one of these lines. Okay, so that's what a stage looks like. If you go over there, as a matter of fact, I think they're putting one of the columns back together. If you go over there before they finish, you'll be able to see the whole thing. So, we are going to try and devise a rough way of calculating what something as complicated as that is trying to do. So that's our aim. Our aim is to try and decide if we can make predictions about something that looks like that. So, what can we do? And we'll do some crude things. First thing we can do is we can say, well, suppose a column like that has been built. Okay, if a column like that's been built, I know n number of stages, and I know f the feed stage.
Yeah.
I know if the column's sitting there, it's been built within the number of stages f the feed stage. I'm certainly going to assume I know the feed rate, the feed composition, and the feed enthalpy. So I imagine I know the feed. Now, here's what I know. I know I've got 2 degrees of freedom per stage. And so how am I going to use my 2 degrees of freedom? I'm going to set the Q's on all stages equal to 0. I'm going to set the Q at one end equal to whatever I want it to be. I'm going to set the Q at the other end to be whatever I want it to be. Okay, I've used up 1 degree of freedom per stage by setting all the Q's. I'm also going to set the pressure, and I'm going to set it the same everywhere. Okay, having done that, I've used up 2 degrees of freedom per stage. And therefore, I imagine this column does something. So my job at this point is find out what it does. That's my job right now. But I'm not going to do this job. This is the job we always did first in all of our other problems, but as you know, this is a trial and error, and I want to set up the basic calculation before we get into a trial and error, so I'm going to make some trades. So I am going to trade 2 variables that have already set, and I'm going to unset them. So I'm going to unset N and unset QB. Give up N, give up QB, and trade those for 2 product specifications. That's what I'm planning to do now. This is so when I trade it for 2 product specifications, I'm now going to find N and I'm going to find QB to make those 2 product specifications come true. So this is the game we're playing. So the first thing I'm going to do is I'm going to take a look at this thing and see what material balances around the column require of me. So let us take a look at material balances around the column, and that will tell us what the easy problem is, and that's where we will start. So let's take a look at the material balances around the column. How many are there? There are C of them. That's how many material balances there are around the column for a C component system. How many equations are there? The equations that involve variables around the column are 2C minus 1 plus 2, which is 2C. So I've got 2C variables around the column, and I've got C equations. But I'm going to add to these C equations two product specifications. So I've got C plus 2 equations, the C material balance, and the two product specifications, and I got 2C variables. So the first question we ask is, when is C plus 2 equal to 2C? When is C plus 2 equal to 2C? And the answer is C equal to 2. So we start with C equal to 2 problems. C equal to 2 problems are easy, and you can begin to see why. I can take a C equal to 2 problem with two product specifications and make all the balances around the column to begin. At C equal to 3, I cannot do that. So let us see where we stand. I now say that a standard problem that we want to solve is one where, so let me point out clearly what the problem is we would like to solve. I set the feed. That means I set F, I set Z, and I set HF. I got C equal to 2, so I will work entirely in terms of a more volatile component. So I set the feed. I set two product specifications. For example, I can set the purity in the overhead, YD. I can set the recovery in the overhead, YDD divided by ZF. So I've set the purity and the recovery in the overhead. I, of course, am going to set the pressure. And we recognize that F equals C minus P plus 2. C is 2, P is 2, so there's 2 degrees of freedom. I've set the pressure, so that puts me at 1 degree of freedom. That means whenever I assign a value of X, I can get a value of Y. X will be my 1 degree of freedom, Y responds. So I start this problem with an equilibrium curve. So here it is. I start this problem plotting Y up this way, plotting X over this way. I start this problem with an equilibrium curve. I'm entitled to that. I go get it somewhere. I'm given it. I go find it. I learn how to predict these things. Whatever it is I learn how to do, I go do it. But the pressure's set. I'm entitled to this equilibrium curve. E is set. All equilibrium points, therefore, lie on the Y.